So thank Andy for introduction. I'm Xuan, and in this talk, I will introduce a glass-free DIY 3D display that you can easily build at home, and it can make an object appear as if it were right in front of you. So this is how it looks from the back perspective. And this is the whole setup. Our work is inspired by YouTube videos showing how to achieve similar effects with those pyramid reflectors. These are often referred to as the Pepper's ghost illusion. So back into the 19th century, Professor John Henry Pepper, he managed to put a ghost on top of a stage. And the ghost can move, can act, and it's really cool. And so the trick was the actor or the actress is actually underneath the stage, and it was its reflection that's on top of the stage. So that's also why our work is called the Pepper's cone. These Pepper's ghost illusion with those pyramid reflectors are surprisingly compelling. However, they only support up to 4 set viewpoints and introduce distortions when viewed from the wrong perspective. And so basically, it looks very planar and it's not 3D. So apart from these DIY 3D displays, there are also many other 3D display prototypes from the lab settings. These are all very cool and creative work. I just list a few here. And with those 3D displays, you can really visualize 3D objects in 3D, and you can do cool stuff like teleconferencing, etc. However, typically, they are large, complicated, and expensive. Wouldn't it be cool if we can create 3D illusion, but with simple, available materials, and you can do it at home? And that's our goal here. We seek to provide glass-free 3D illusion while maintaining a DIY setup. Our setup requires only an iPad, a thin plastic sheet that costs about like a couple of dollars, some tape, and a nickel. Here's how it works. So we start with placing the cone at the center of the iPad. Suppose this is the image you want to show. If you just show this regular image on the iPad screen, its reflection will appear distorted. So some sort of distortion calibration is required. Therefore, what you can do is you can first pre-distort the image so that its reflection appears undistorted when viewed through our display. So how should we do the pre-distortion? Let's consider a single pixel from the iPad. A ray from it got reflected and reaches the eye. If we consider the eye as a camera and taking some picture, then what we want to know is the mapping from the iPad image to the camera image. To capture this mapping, we use a method similar to the environment mapping technique. So this is the display. We place an iPhone at desired eye location. And we capture a... Oh, the video doesn't play. And we captured a sequence of green magenta stripes using using the iPhone. And this is the iPad. Sorry, the video has some problem, but this is the iPad. This is the iPhone capturing it. This is the reflector, and it captures the reflection. This is a sample image from the iPhone. The green and magenta stripes here serve as binary code, so 0 and 1s. And after you play a sequence of them, each iPad pixel is assigned a unique binary code. And if you look at one camera pixel, for example, you can decode this binary code, and then you can figure out from which iPad pixel it comes from. So in this way, we know the mapping. And we know how to pre-distort for one orientation. And since the cone is rotational symmetric, we can apply the same pre-distortion for all the angles. And by using the gyroscope to track rotation, we can figure out the correct view from that orientation, and we can pre-distort the image and show it on the iPad. And what's really important here is that we want the rotation estimation to have really low drift and low latency. Otherwise, after several rounds of rotation, the object would drift away, or the object would appear to follow you instead of you feel like you're rotating the object. And we can also show animated 3D scenes. And add audio. Audio one. So this is supposed to be my voice saying, "Hi, I'm a virtual assistant." I don't know what happened with this. We can also show real object captured with camera and turntable. A variety of reflector is possible. Even something as simple as a plastic cup can work. So a cone can work, as well as many other reflector shapes. So what is the best reflector shape? Whether it's a cone or something else. If a cone, what's the best parameter? What's the best angle, radius, height, etc.? And what's the notion of best? How do we define best? So to answer this question, we analyzed a set of reflectors. We focus on rotational symmetric reflectors because we want seamless rotation, and it can provide simpler calibration because the pre-distortion can be the same for all the angles. And in particular, we focus on conic reflectors, including ellipsoid, cone, paraboloid, and hyperboloid. And we found that different reflector shape can affect people's ability to fuse the images received from the left and right eye. So to really understand this, we need to introduce a concept called vertical parallax. When you look at our display, this is the left and right images you will see by your left and right eye. And ideally, corresponding points should lie on the same horizontal line. However, with curved reflectors, it's not necessarily the case. And there typically exists such vertical parallax. Previous research has shown that when vertical parallax exceeds half a degree, for example, it's hard to fuse. So we analyzed the vertical parallax of a cone, for instance. And so this is the cone. And given the viewing points and the display size, we can figure out within which region we can receive reflection, and we can compute the vertical parallax within that region. The color here indicates the vertical parallax. So blue means good, low vertical parallax, easy to fuse, and red means bad, large vertical parallax, hard to fuse, and typically in the center, the vertical parallax is small, and as it approaches the boundary, the vertical parallax is larger. And this black curve here encloses the region where its vertical parallax is below half a degree. So this is the fusible region. If you want to display an object, it's better for its reflection to appear within this region, and or at least its important part should be within this region. So this region is actually indicative of some notion of effective display size. Because beforehand, we do not know whether the object to display is tall or wide, we use a circle, the maximum inscribed circle within this region as the effective display size. So here's another reflector with its effective display size, and you can see that the size is different for different reflector shapes. So our goal here is to maximize this effective display size and to maximize this circle here. Is it okay that I restart because somehow it works. So we also analyzed the vertical parallax of other reflector shapes, other conic reflector shapes. So now you can see how the effective display size changes as the reflector shape changes. So here I just give some examples. And with our method and criteria, we can figure out what's the best reflector shapes for different configurations. So for example, for a 12.9-inch iPad Pro, a 51-degree cone is the best. There are some limitations of our work. A crucial illusion we want to create is that the object is actually floating inside the reflector. So it's very important that our stereo depth perception reinforces that. However, it's true that our display does not show the depth that you would expect from the object to display. But in our paper, we show that your stereo cue do tell you the object is actually inside the reflector. So to address this stereo depth perception problem, we extended our display with red cyan anaglyph glasses to show the correct binocular images. So here we show a red and a cyan image, and the two images are calibrated towards your left and right eyes separately. Although this display can show the correct depth, but based on our user study, we discovered that people still prefer the previous system because of its simplicity, convenience, and color quality. And more interestingly, users reported the 3D-ness they perceive from this system and the previous system is actually very similar. Another limitation is that the system works the best when viewed from the best perspective, the calibrated perspective. But as long as your head is centered horizontally, changing the distance to the display or changing the height does not affect the distortion much, so you will still see the image undistorted almost. But when you move your head horizontally, you do perceive some tilting effect. Despite the limitations, a variety of applications are possible, including medicine, so doctors can explain to the patients their heart disease by showing the 3D models of their heart interactively. It can also be used in animation. Archaeology. Education. and product exhibition. An extension to our system is adding camera-based head tracking. If we can do head tracking really well, this is the effect you would expect. So as mentioned, one limitation of our work is that it works the best when viewed from the calibrated position. But if we can do the head tracking like really real time and really good accuracy, then you can see the 3D illusion even while moving your head freely. And it would be cooler if we can do it, we can achieve very low latency, low drift, while maintaining a simple setup. Some other work can be explored, for example, interaction, like how to scale it for large display, etc. So our code will be open source soon, and a tutorial on how to build a clone yourself will also be released at the webpage. If you're interested and want to be notified when it will be released, you can email me. Pepper's clone is a very simple DIY 3D display that you can easily build at home. And we really want to spread this experience to everyone. So if you're interested in our work, we invite you to follow the instructions and build a Pepper's clone yourself. Thank you.
A couple minutes for questions. Any takers? So I'll kick things off with a question. I think, let me just use the mic. I think one of the interesting things about this work in the paper is actually a really nice exposition of a lot of different camera calibration techniques. And although I think the overall effect here is quite simple, the paper actually has a lot of value in how it presents all the different things that come together. And so I think actually if you're out there kind of teaching these kinds of concepts, I would suggest taking a look at this paper. And the fact that you have something that's easily replicable, I think it would be fun for students as well. The interaction part, I think, is sort of an obvious one because I see you touching the display, and so that's sort of one thing. And then I wonder if you've thought about how much more complicated would it be to add camera tracking or person tracking using the built-in front-facing camera. If you think that you can actually do that, I'm trying to imagine what that image would look like with just the simple materials that you have today, just not using sort of fancy reflective materials, but just the sheet of, I guess it's a acrylic, plastic?
PETG plastic.
Yeah, so I'm wondering if you had tried that and what that sort of looks like.
I have tried the front-facing camera, and I even added a fish eye camera on top of that. Some problem with that I still haven't solved is, first, when the camera is looking up, most of the image is occupied by the ceiling, for example. So the resolution of the boundary where you can see the face is kind of limited. And the head have very strong distortion, so we need to undistort that to account for that. So it's still possible that it can be done, but I'm still experimenting with that. Another possibility is that at the center of the cone, you can add a simple camera, and it has a mirror on top, and you face up, and it receives the reflection from the surroundings, and you can have some camera face tracking. Yeah.
Sorry, Tim Dwyer, Monash University. What's the largest display size you could create with this technique?
It really depends on the size of the plastic sheet that you can bought. The one I have created is like this size. So it depends on the plastic sheet size and the display size. It can be larger, but then you would need a larger display size. So it's an interesting direction to see, like if I explore other reflector shape, would I be able to have even smaller display size while a larger display size, a larger effective display size.
I guess also the brightness of the display limits the effective range of the illusion, right? If you really,
Sorry, it's too, voice it too low.
Yeah, sorry. I guess to make it significantly larger, you would also need to make the display much brighter. So not just make the display bigger, but also brighter.
Yeah. It's also very important. Yeah, so in the environment, like how bright the surrounding is. So different materials can be possible. For example, something less transparent. We do want the transparency, but it can be a little bit less transparent so that you can have more reflection. So the material can also be explored to see how to achieve better contrast. Yeah.
Thank you.
Thank you.